Section 11.5, Mathematical Induction. What is mathematical induction? Mathematical induction is one of the many methodologies used for proving mathematical hypotheses. Specifically, mathematical induction is used to prove that a statement is true for every natural number n. So in this section, you are going to get a taste of mathematical proofs, okay? People who study mathematics, higher level mathematics, like math majors and stuff, there is a point in time where like the numbers pretty much go away and all you work on is math theory. Okay, so basically everything that you've learned in your entire math life, it's been proved somewhere to be true. For example, the quadratic formula. Someone had to come up with it and prove that it holds true for every quadratic equation that you deal with. Okay, so there's this whole art of doing math proofs. Induction is just one of the many ways you can do a proof. Specifically, induction is used if you're trying to prove a statement over the natural numbers or the counting numbers. Okay, so before we jump into the first page, what I have mostly on the first page is basically an explanation of how induction works, okay, and how you can think about it. We're going to jump to page 2 and talk about why mathematical induction is necessary. Okay, so once you get an idea of the kinds of statements we're working with and why induction is needed, then we'll go back to page 1 and talk about the process of mathematical induction. Okay, so at the top of page 2, why is mathematical induction necessary? Okay, here comes our first statement. This is going to be a statement over the counting numbers. N will represent a counting number here. And these are the types of statements we'll be working with in this section. Okay, you'll have to basically prove these things are true for any counting number. Okay, so here we go. It says let Sn, and hang on a second, this is not related to sequences in series. Okay, when you saw Sn in sections 11.1, 11.2, and 11.3, this referred to the sum of the first n terms of a sequence. Okay, this is a different Sn when you're dealing with mathematical induction. It is representing a statement for a natural number n. Okay, so let me write this down. This is referring to a statement involving the natural numbers. Okay, so yeah, it's the same notation, but they mean totally different things here. Okay, so it's a little confusing. Okay, so we're going to let Sn represent the following statement. Okay, Sn, the statement is 2 to the nth power is less than or equal to 2 times n. Okay, this is the statement we're working with right now. Okay, 2 to the nth power, is that always less than or equal to 2 times n? Okay, if you read what I have below the yellow statement, it says this statement is not true for every positive integer n. How would we prove this? Okay, so basically what this sentence right here is saying, this yellow statement is not true for every single natural number. Okay, it's true for some of the natural numbers, but not for every single one. Okay, how would we prove that this statement is not true for every single positive integer, for every single counting number? Okay, it's actually easier to prove something is false than to prove that it's true. Okay, to prove that something is false, all you have to do is find one instance in which it's not true. Okay, so I'm going to write that right here. To prove something is false, just find one instance in which the statement is not true. Okay, so that's what we're going to do here. We are told the statement is not true for every single counting number. Okay, so we need to essentially prove that. Okay, So here's what we're going to do. I'm going to start with the first counting number. Okay, the first natural number is n equals 1. And I'm going to keep plugging in counting numbers until I find one for which the statement is false. Okay, so if I plug in n equals 1 into this yellow statement, I'm going to get 2 to the first power. Is that less than or equal to 2 times 1? Okay, well, that's going to tell me that 2 is less than or equal to 2. That is true. Okay, so the statement is true for n equals 1, for the first counting number. Okay, well, does it work for n equals 2? I don't know, plug it in. Okay, everywhere you see an n, replace it with 2. So you're going to get 2 squared is less than or equal to 2 times 2. Okay, if we simplify, this is going to tell us that 4 is less than or equal to 4. Okay, that's true because any number is equal to itself. Okay, so the statement is again true for the second counting number. Okay, now I'm going to bump it up to n equals 3 and see what happens. Replace n with 3. We're going to get 2 cubed is less than or equal to 2 times 3. Simplify. I'm going to get 8 on the left. Is 8 less than or equal to 6? No. Okay, so the statement is false for n equals 3. Okay, and I'm sure there's another counting number out there that it's false for. Okay, like if you checked 4, 2 to the 4th. Okay, is that less than or equal to 2 times 4? If I simplify this, 2 times 2 is 4 times 2 is 8 times 2 is 16. This would be saying 16 is less than or equal to 8, which is again false. Okay, so you don't have to keep finding other false instances. As soon as you find one n value for which the statement is not true, you're done. Okay, since this statement is not true for n equals 3, okay, that means it cannot be true for every single positive integer n. Okay, so let me write that out to the side. Okay, so since the statement is not true for n equals 3, then it is not true for every, let me see how it was worded up here, every positive integer n. Okay, since the statement is not true for n equals 3, then it is not true for every positive integer n. Okay, so again, if you're, to prove something is false, really easy. Just find one instance, one counting number for which the statement is not true, and you're done. Okay, however, if you're trying to prove that a statement is true for every single counting number, it's a lot more complicated. Okay, so if you read the next bullet point here, it says in section 11.1, we accepted that the following statement Sn is true for every positive integer n. All right, this is one of the summation rules that we saw. Okay, the one where if you add up the first n positive integers, okay, 1 plus 2 plus 3 plus all the way up to n, if you add those guys up, the sum is equal to n times n plus 1 over 2. Okay, so this statement, like I said, we just accepted it. I didn't do a proof. I did tell you we were going to look at this when we got to mathematical induction. Okay, this statement is true no matter what the n value is. Okay, it's true for every single counting number. How are you going to prove this? Okay, well, you can do what we just did. Okay, above, we started plugging in counting numbers to see if we got a true statement. So, you could do the same thing here. So if n is 1, S1 would be 1 plus 2 plus 3 plus, well, that doesn't really, I went too far, okay, because you've really got to pay attention to your notation here, okay. On the left side, you're adding up the first n many positive integers. So here you'd be just adding up the first positive integer, which would be 1, okay. Is that equal to, your n value would be 1 here. On the right, plug in 1 for n. Is this equal to 1 times 1 plus 1 divided by 2? Okay, well, is it? this is going to tell me that 1 equals 1 times 2 divided by 2, which tells me 1 equals 1. It's true for n equals 1. Okay, then I could test another counting number. Okay, what if n is 2? Okay, well, this is going to be, let me write this here. This was S1, the first statement. S2, okay, if n would be 2 here. Okay, so we're adding 1 plus all the way up to n, which is 2. So we'd be adding the first 2 counting numbers here. Okay, is that equal to 2 times 2 plus 1 divided by 2? Okay, again, on the right side, I'm just plugging in n equals 2. Okay, so we're just trying to verify that this statement is true for an n value of 2. Okay, if we simplify on the left, we're going to get 3 is equal to 2 times 3 divided by 2. That's 3 is equal to 6 divided by 2. And so yes, 3 is equal to 3. It's true here. Okay, and you could keep plugging in. I'd plug in another one. Okay, n equals 3. Okay, so the statement S3. Okay, on the left side, I would add 1 plus every positive integer all the way up until n, which is 3. So I'd be adding 1, 2, and 3 here. Okay, is that equal to this right side? Replace n with 3. So is that equal to 3 times 3 plus 1 over 2? Okay, if I simplify both sides, 1 plus 2 plus 3 is 6. Okay, is that equal to 3 times 4 divided by 2? Okay, well, yes, if you simplify, this is going to be 6 is equal to 12 divided by 2. So 6 is equal to 6, which is true. Okay, and you could keep going. Okay, but how can you possibly do this? If you're trying to prove that this works for every single counting number, you'd have to test out every single counting number. Maybe this statement fails when n equals 1,000. Maybe it fails when n is equal to 1,000,000, but it works for everything that came before it. Okay, so when you're proving that something works for every single counting number, this is not a viable way of doing it. Okay, because you can't test every single counting number because there are infinitely many. Okay, so in a situation like this where we are trying to prove a statement is true for every single counting number, we are going to use the process of mathematical induction, okay, because it is a concise way of showing that a statement is true for every single counting number. And you can't, you don't, in the process, you don't test every single counting number out because you can't do it. Okay, it's just not possible. Okay, so now we will turn back to page 1 and talk about how the process of mathematical induction works.